Okay, into the final subtopic for the light and matter topic, and that is the wave behaviour of particles. The main application we're going to explore in this topic is electron microscopes, which is basically a technique that lets us get really cool images of things like insects, like this one shown here. So the first thing I want you to do, and I do really want you to do this, is download the notes, copy and paste this link here firstly into your browser and watch this TED-Ed YouTube video. Then after you've watched that one, I want you to do the same thing and watch this second video. I'm not going to say too much on the background of this stuff. Those two videos will tell you the story in a much better fashion, and they'll build the picture up from what we've looked at in the photons topic. So, pause the video, download the notes, go away and do that. Okay, I've trust you've gone away and looked at the videos now, and you're feeling a little blown away, although maybe not too blown away, because I might have given away what the story was that was coming already. However, it is a very interesting and slightly mind-blowing concept, this idea of that not only does light behave like a particle, but particles also behave like waves. And I guess, you know, the most common property we use to characterize a wave is the wavelength. So now we have this formula here which tells us the wavelength of a particle. So the wavelength of a particle is equal to Planck's constant divided by its momentum. Now typically when we talk about particles, particularly electrons, we tend to talk about their energy. We talk about voltage and accelerating them across voltage and how much energy they get. And then from that energy, we can use the kinetic energy formula to work out their velocity. And by extension, we can go through and rearrange that formula to get that in terms of mass and velocity. And we know that mass times velocity is momentum. So this little exercise here lets us find the relationship between the energy of a particle, and its mass obviously is important, and the amount of momentum that it has. Because when we start dealing with the de Broglie relationship, this one here, we need to know about the particle's momentum as opposed to its energy, which we might usually deal with. That's probably the most important thing to take away from this slide. Solving problems with this equation, which is what our intended student learning is usually a fairly straightforward process once we can understand that. So I'm sure you're now asking yourself, how did they prove, in inverted commas, that the particles can behave like waves? And the initial experiment that really showed this was the Davisson and Germer experiment. There's a great simulation at PhET for this experiment, and I would encourage you to go to that link and have a play with that simulation. This is a screen that you sort of get from that simulation. But in essence, what Davisson and Germer did is they fired low energy electrons at a nickel crystal. Now this nickel crystal had evenly spaced atoms, and it in a sense acted like a diffraction grating. Now what we were dealing here with was a reflected pattern as opposed to one that was transmitted like we did in the lab. We don't need to understand the difference between those two, but the similar principles apply for a nickel crystal. It acts like a diffraction grating, and we can see a diffraction pattern, so a series of high intensity and low intensity peaks in the reflected beam, as you would expect to in a transmitted beam from a diffraction grating. So they fired these electrons at this nickel crystal. They saw this diffraction pattern, so they saw that there were certain angles at which you saw a much higher intensity of diffracted electrons. They then used the relationship that we've already used for a diffraction grating, and they calculated the wavelength here for those electrons. So because they saw a diffraction pattern, that's a wave behaviour, the idea of interference, constructive and destructive interference. So therefore you can apply this equation and calculate a wavelength. Then what they also did is they calculated a wavelength using de Broglie's relationship. And they could do that from knowing the velocity. So the velocity they could work out from the voltage or the energy that the electrons had, momentum equals mass times velocity, or you could use that relationship we talked about on the last slide, and then they were able to work out a wavelength for those electrons using the de Broglie relationship. And voila, lo and behold, whichever term you like to use, they found that there was both these techniques gave the same answer. So this was really, really strong evidence to support the hypothesis that electrons were behaving like waves. So you need to be able to do some problem solving with these two techniques, calculate the momentum and therefore the wavelength, calculate the wavelength based on the preferred angle of reinforcement, and basically describe this experiment that they did to show that waves were behaving like particles. So let's talk about the application for this subtopic, and it is a really, really neat one. It's one that I must admit I'd used quite extensively when I was a scientist before I became a teacher, and it is one of the most common tools in a lot of laboratories, and that is an electron microscope. So why would we want to use an electron microscope? I've got two examples here. We don't need to know about the difference between a transmission and a scanning electron microscope, but that was just the best picture I could find. So what's the difference between an electron microscope and a light microscope? So you're probably familiar with a light microscope that you use in the lab, and you put your sample on and you look through a magnifying lens, and it basically magnifies that image that you're looking at. Now, probably the first and most important concept to introduce here is the concept of resolution. So resolution is the ability to distinguish between two separate points. So I use these two here as an example. I think most of you could see, hopefully it comes through in the video, we don't lose too much quality, that these are clearly two separate points. So our eyes can resolve those into two separate points. However, if you look at these two here, particularly if you look at it from a bit of a distance, they just appear as one point. But I can assure you there is a fine line between those 2 points. They are not actually one single point, they are two separate points. So when we talk about resolution, we are basically talking about the ability to see fine detail. So the ability to resolve that fine detail by resolving between 2 points. Now, the resolution that can be achieved with any type of microscopy or any type of light, for lack of a better term, is related to the wavelength of the radiation being used. So the shorter the wavelength, the greater the resolution. So if you have a large wavelength, that means you can only resolve things on a large scale. If you have a very, very small wavelength, you can resolve things on a much smaller scale. So the maximum theoretical resolution, as I've just said, is proportional to the wavelength being used. With visible light, this is about a micron, or just under a micron. You know, visible light's around 500 nanometers, which is half a micron. So 10 to the minus 6 meters. With low energy electrons, the wavelength of those, and we can calculate those using our de Broglie relationship, is about 10 to the minus 10 meters, or a tenth of a nanometer. We're almost getting, well, we are getting down to the scale of an atom. Atoms are on a sort of sub-nanometer scale. So we can get much, much higher theoretical resolution. Very hard to reach the theoretical resolution with any technique, but obviously this is going to give you a much better chance, and it does give you much better resolution, the 10 to the minus 10 meter radiation, even though it's particles, but we know they're almost the same thing, compared to the light at 500 nanometers. So the wavelength is really important in terms of giving us resolution. We can achieve those really, really small wavelengths by using electrons rather than using light. Just related to that, if you look at a typical electron micrograph or electron microscope image is probably what I should call it. It'll look something like this. This is an electron microscope image of blood cells. And on those, you can hardly see this in this one, but you'll normally see a voltage down here. So this one was taken at 10,000 volts. So that voltage lets us work out an energy from work done equals Q delta V. Once we work out the work done, we know the kinetic energy, we can work out the velocity, etc. So therefore we can work out the momentum of the particles. And if we can work out the momentum, we can work out the wavelength, or the de Broglie wavelength. So, that's part of it, but probably the most important part I need to explain, but I think it's important to understand a little bit about how an electron microscope works before I tell you this, is that because an electron microscope uses a beam of electrons as to opposed to a beam of light, it needs to use electric and magnetic field lenses to focus this beam of electrons. So electrons have a charge so that they can be shaped, if you like, and they can be bent by an electric or a magnetic field. So they use magnets and electric fields to focus the beam of electrons, as opposed to a normal light microscope, which uses optical lens or glass. Glass is able to bend light using the principle of refraction that you might have learned about in earlier years. And that refraction of light as it goes through the lenses is used to magnify the image. However, the electron microscope glass, if you like, won't cause the beam of electrons to bend as such. That in the electron microscope we need to use electric and magnetic field lenses. Thanks.